So, hello everybody. So, welcome to the workshop, paper session on the district. District of Tomorrow. Sorry, and now we will have Selma Causevic who will present her papers. So I let you the floor, and yeah, okay. You want to share your screen? Yeah, you
yes.
can.
Thank you. Give me a second. So share screen and entire screen. Entire screen share. Okay. Now I hope you see the screen. Ah, yes. You see my screen?
Yes.
Do you see my screen?
Yeah.
Yeah?
Yes.
Okay. For some reason, I now hear you not well, but well, my name is Selma Causevic, and I'm a researcher at TNO in the Netherlands, and I will be presenting a paper or presentation on positive energy districts, or actually data-driven approach to aggregate and disaggregate data to model energy balances in districts with mixed topologies. So a bit about the context that we all know is that the modern energy systems are shifting towards more decentralized, sustainable, and smart systems. And because of this heterogeneity and all these changes, well, it is important to understand the effect of these changes. And these changes are mainly brought, mostly brought by distributed energy resource interventions that actually both provide challenges and opportunities for the energy transition. Now, in order to understand this transition and the potential of distributed energy resources and the interventions on the energy balance in smart grids, we have to be able to, we can model them and see how they impact energy balances and things like CO2 emissions or other key performance indicators. Now, one way to do it is to use energy models to understand this impact. However, using energy models can be challenging because it relies on data availability, which is often scarce, especially if we're talking about heterogeneous urban environments where we have mixed topology of consumers, different types of consumers and prosumers, their profiles, different kind of interventions they might have locally or on the district level. So basically getting that data and making sense out of that data and being able to model it on different aggregation levels is what we actually need for the energy models. So this paper actually, or the work we did for this paper, presents a data-driven or data modeling approach to address this, where we tried to combine data from different aggregation levels, from different sources, in order to model individual buildings and individual interventions in the buildings in a district area. And then we wanted to see if we can actually go the other way around, where we have individual interventions, and how we could extrapolate it to the level of a district in order to see what the impact of the different demands and the different interventions is on a district area. How it impacts energy balances, CO2 emissions, for example, and positivities, let's say, of a certain urban environment. So we use that as a use case in a project called Making City, and for a city of Groningen, where we looked at 2 districts. The first step was the work, actually the most work that we did was in estimating energy balance in urban districts, and that was on modeling supply, on modeling the energy demand. What we did is actually we use an open source in-house built modeling language called Energy System Description Language, and the tool suite surrounding it to model 2 of these districts. This tool suite actually is used to both plan and design for different kind of energy transition scenarios. and you can use it you can basically describe an energy system in a unified way. We can also run simulations in an interactive map. Actually, we can create a system, and then with a tool in the back end, as is Energy Simulator, we can run the simulations and see the balances, different KPIs, and like CO2 emissions and others. So what approach did we take? We went from the district level to the building categories level, and then to the individual buildings. So we looked at the entire district, and we realized that different kind of building categories have different consumption patterns, different profiles, and different consumption per square meter, for example. So what we did is separated a district into clusters according to building categories, and we actually used different sources to look at the service sector consumption for different service sector categories, and statistical data on residential load demand. From there, we went also to the individual building level, disaggregating further. And as for the production data, it was mainly modeled using existing technical documentation and also statistical data on residential PV, but this is specific for the PV. So that's how disaggregation was performed and load was estimated. However, what we were interested is how we could take this step further, or how we could go from disaggregated or individual level in building data to the district level and see the effect of interventions on district level. So basically, we designed a methodology that uses individual interventions to extrapolate on the district level. So the steps of the methodology would be to first identify buildings with interventions within specific clusters of building types, to identify the area where to extrapolate these data to. So this was the service that we use was specific to the Netherlands, but we can also generalize it. So if we have a way to get the information on the surface area of different building categories within an area, we can use that. And then we can also cluster this area further according to different building parameters, such as category, floor area, maybe facades and the rooftop, and so on, to get more specific, for example, information on different buildings. Then this identifies clusters containing intervention buildings. Then building energy data can be estimated if not specified. So this would be load demand data actually. Then basically the interventions would be a number of interventions would be chosen from the specific building. For example, if they have a rooftop installed, so we can choose, okay, how do we extrapolate PV to other similar buildings? And using different parameters, basically, we can say that for a specific building category with specific parameters, with a PV rooftop area of a certain potential, we can find a similar building, and using statistical extrapolation, we can actually see how we could, what would be the specifications or energy balance for a similar type of building. And then finally calculate the KPIs. So this is actually more of a work. This is actually a work in progress. So this part we do not have implemented, but this is the way we would propose how to go from an individual to an aggregate level of to get energy balances. This was applied on a use case in Making City project, like I said, and here you can see the two models of the two districts where we modeled different, the blue are energy demands, for example, for heat and for gas and for electricity, and different conversions and different production sites. And there we got, by running this, so this was modeled according to the first step of aggregation. disaggregation, and then we were able to get insight into our energy balances and CO2 emissions. So this was a very actually brief presentation on the work we did. And then we realized it's already through the project, we realized how difficult it is to get the proper data, to try to make energy models, hybrid energy models of an entire energy system with the existing data. So we tried to find a way to aggregate and disaggregate data to be able to see the impact of different interventions for future urban districts. We had several actually experiment results, but I didn't put them here in the presentation because it's quite detailed hourly data. But then the next step would be actually to see how we could go the other way around. So thank you for your attention. And then I will stop sharing. I do not hear.
Now we can hear you. Okay. Thank you. So thank you very much, Selma. It was a very interesting presentation. And now we have to jump in another presentation. If somebody have question, you can use the chat to share your question. So now we will welcome Tony Castillo from the University of Deusto, who will present his paper on e-mobility.
1 second, we're just going to refresh the screen. Okay.
I think it would be a very good opportunity to get in touch and compare approaches to text modeling in that sense.
Okay, Selma, I don't know if you have heard the question from the room here. It was the representative of the PED project from Atelier. And it was very interesting to share the vision with you, and maybe we can contact each other at the end of the project. So, okay, so now we will jump in another presentation from Tony.
Yeah. And swap. Can be our, yeah. And now you're all set. You can talk.
Oh, no.
You'll only see.
Is
Yeah, it's good.
oh, okay.
Oh.
Sorry. Okay.
Go back to the slides.
No.
Yeah. Okay.
Is it okay for me to
So you're
start?
all set. Okay.
But they see this.
Yep. They
What?
see, no, they see this and you.
Hello?
Hello, good afternoon. My name is Tony Castillo. I come from Spain, from the University of Deusto. I'm actually currently working in Atelier project. I'm going to make a very brief speech about the impact of e-mobility in positive energy districts. This presentation is outlined as usual. We can find a proceeding: introduction, materials and methods, some results and discussion, conclusion, and future work. Well, what is the introduction of this rising problem? As many of you know, mobility is the third sector in greenhouse emission worldwide, just right after electricity and also heating system. This is a promising solution because e-cars can avoid the use of fossil fuels, and as a consequence, they don't emit greenhouses. But the inclusion of electric cars have great impact on energy grid because they considerably increase the requirement of renewable energy generation system. This has to be considered in urban planification. So, some studies remark that electric vehicle smart charge system could significantly reduce distribution network costs in low carbon transmission pathways. Electric vehicles greatly impact on energy efficiency since they can be also used as battery and also can help to smooth peak hours consumption. Alongside, this technology is easily integrable in urban scenarios like the presented in PETs. The importance of electric vehicles rise when we take into consideration demand side management, and also in Atelier project has been remarked the importance of the flexibility of the microgrids. Another important aspect that the electric vehicle add to the PETs is they can help to sort out the fluctuation of RINA. Well, as we know, PETs require integration of different systems and infrastructures and interaction between buildings, the user, and the regional energy, mobility, and ICT system. This is part of the definition, of the current definition of the PETs. So, in a PET, summarizing, is a district that produces more energy than we need to meet for the people who live there. Well, which is the motivation? Our motivation is, despite its agree, is to take into account the mobility system with its own share of energy needs. It doesn't work unless we haven't found any criteria for how much of each user's mobility energy shall be produced by the PET. The aim of this research is to assess the impact of electric vehicles might have on a testbed PET. Well, the first step was setting up the PET, where it's gonna be deployed. Even this project has 2 lighthouses. In these cases, is deployed for Bilbao. Bilbao, as the majority of the city of Europe, it has a very consolidated urban areas, but in Bilbao there is, as you can see there, an island who is partially isolated from the rest of the city. This whole area was in the past for the industrial use. So this is a gray area with many buildings who are in not good conditions. So that's why Atelier has focused on this island in order to make something that we in Bilbao name as urban lab. In this area, we will set up 3 districts: north, south, and center. So after setting up the district, the PET, we decide to use the PVG's information tool to set to be aware of the amount of the irradiance energy, solar irradiance on the island. After taking the information of the PVG's tool, we realized that May is the month with more irradiance along the year in Bilbao. So then we, using some techniques, we decide to take some aggregated values from best tables to model the type of building we are going to include in our synthetic PET, residential and service. Both of them has different profile of consumption. now only I'm highlighting the residential one because it's the one who rise the challenges. So because in the night we don't have RINA production. Additional to this, it's important to highlight that we use the performance energy of the buildings for make our assessment. The PET was architected in my lab, okay, using the first laws Kirchhoff for defining if we have or not surpluses at the end of the year. The model was constructed using or calculated using Ohm's law for every single element of our PET. I mean, heating system, cooling system, hot domestic water, electricity generation, and so on. Sorry for this in Spanish. Well, in this case, we calculate making some assumption the number of cars that might be into the PET. We figure it out. In this case, we calculate about 400 cars. We prepare a pool of 8 different scenarios to test our PET archetype. Well, after making some simulation on my lab, we noticed that we had a lot of problem on January. Well, in the as the vast majority of Europa, in the winter and spring months. On the other side, we have the summer months. But we noticed that May, even is the largest, which is the largest month where we have, we are about to set to match the radiance of a standard test condition is 30% below a standard test condition. Well, we made 2 tests, one for the worst month of the year, and in this case was January. And in January, we are not able to achieve the positivity, and only for 3 hours the energy storage system is being charged. So it means in only during 3 hours we got positivity. It's not possible to consider this month as positive. So in May, on the other side, in May, we got positivity because we were able, as you can see here, as you can see here, the battery system is getting energy during 12 hours because there are a lot of surpluses when you take into consideration power consumption and PV system generation. So these are the 8 scenarios we test out. These were PV system included or not, energy storage system included or not in the simulation, light system, smart poles, because they not only give light, they are in charge of sensor humidity and so noise and some sort of variables that we want to measure, or changing to LED 1. Energy label, which is the core of this analysis, the performance in the isolation of the building is quite important because we know that this older building need to be retrofitted in deep. So at the end, we only got 4 scenarios that where we can achieve positivity from 5 to 8. Here we have the yearly balance, PET balance, where we can see scenarios 5, 6, 7, and 8. All of them achieve the positivity. So the difference between scenario 5 and 7 is only the isolation certification for building who rules this sector in Spain. And it's the same for scenario C and 8. Scenario C is B, meanwhile scenario 8 is A. So it means this has the highest performance use in energy consumption. So at the scenario 5 and 6 only differs in which, meanwhile, scenario 5 doesn't include electric charger hub. The scenario 6 included. It does include it. So in the bar plot, we can see we have more positivity in scenario 5 than in scenario 6, and the same happened to 7 and to 8. So at the end, we decide to explain only these two scenarios, 5 and 7. Why? Because in the two others, we don't have exactly the number of vehicles that we can attend. Meanwhile, in this 5 and 7, in this case, 1 and 3, we can. So you can see here that we have more surpluses here is due to this has a better performance than this one building. In this case, you can see that the distribution of the consumption of the PET month by month. Then we have the same for scenario 6, where you can see how the electric vehicle consumption is set as fixed number. Conclusion. We can conclude that it's possible, running in this way. I forgot to tell you that a scenario 5 can meet the number of vehicles that are supposed to be into PET boundary. It's about 400. Meanwhile, scenario 7 produce energy to attend 150 vehicles outside of the boundary of the PET. So this can be a starter point to maybe establish a new business model and use those extra energy surpluses to be sold. And well, conclusion, we can conclude that it is possible to achieve the positivity of the district, and in consequence, this energy surplus could be used to meet mobility demands of local residents, or even, under some scenario, to electric vehicles that would be passing by. The key parameter is the energy efficiency level of the building. It is remarkable that we achieve the positivity once we have enhanced the efficiency of the building, unless to be. And in the end, the PET might provide as much as about 7 million of green kilometers, which can be turned into 545 electric vehicles in the best scenario of the PET. Future work. In this technical work, there are plenty things to do still, so we are open to receive any insights to help to improve the model, and so you can contact us through these emails if you want to collaborate with me. Thank you.
Thank you very much, Tony. And now we will welcome online Rudy from the Municipality of Amsterdam, who will present the project Atelier.
Yeah. Can you hear me?
Yes, I can hear you, but I try to make you presenter. I don't know.
He can do that himself.
Okay. So you can be presenter now. Can you present your screen?
I'm going to try. You can see it.
Okay, yes.
Then I'll start the presentation. Is it okay like this? Hello?
We are a bit late, so if you can shorten a bit your presentation, it will be very welcome. Just 1 minute left. Thank you.
Okay. So what can be expected from this presentation? Some general information on the project, description of the demonstrators, our experience, and maybe I will be a little bit shorter about the other atelier city-oriented activities like city visions, innovation ateliers, replicability, and citizen engagement for the sake of time. But the information in the sheets is might be helpful for further reading. So what are the goals of our project? We endeavor to demonstrate positive energy districts. There are 2 lighthouse cities in there, which is Bilbao with the island of Zoro, which was also featuring in the previous presentation of Tony, and Amsterdam. And we also have 8 or 6 fellow cities, being Bratislava, Budapest, Copenhagen, Krakow, Matosinhos, and Riga. And we try to pave the way for energy positive cities in Europe. So, well, I've already summarized this. In total, we have about 30 parties involved, a duration of 5 years, which may be extended because of COVID. And the Municipality of Amsterdam is the coordinator. So in the 2 demos that we have, I will briefly summarize what is included in that. So our Amsterdam demo consists of positive energy buildings. They are indicated in the graph on the upper right as being Schoon Schip, Republica, and Poppies. 3 building blocks, so to speak. A PV plant for additional renewable energy in the area. And further, we are working on smart mobility, microgrids, local energy communities, and sewage energy recovery. So sewage is a waste stream that we try to, of which we try to keep the energy embedded in the district by producing biogas that can then be burned for thermal use or used for creating electricity. Bilbao's demo is the Zoro Island, which is here in an overview of the entire Bilbao and the harbor area. It is a brownfield island with old industry that needs to be replaced. And you see on this bigger overview the different areas where development is taking place, the north area, center, and south. And also in Bilbao, the ingredients are more or less the same, but an important element in Bilbao is the geothermal energy loop. So most of the energy used on the island for heating comes from geothermal energy that is further enhanced by heat pumps. But we also have an e-mobility hub, smart storage, local energy production, and development of smart grids. So the experience, we started December 2019, and just after 3 months, COVID was a reality. And it affected mainly our demonstrators in two ways. One of the developers in Amsterdam just started the sales of his developments, which was seriously affected by the economic uncertainty. So there was almost a year of delay in the sales of the apartments. and solving the financing challenges for a hotel which was in the area. The site still faces some uncertainties, but if you use the link, you will see a live webcam that is there 24 hours a day. You can see the construction going on. On the demo location of Bilbao, a few of the buildings, the construction works were municipal buildings, and the budget cutbacks in the municipality caused a review of those investments, and they will be delayed, which means that some of them cannot take part in the current scope of the time of the project. The fellow cities are more in like a planning stage, and no direct effects are foreseen. So how did we adapt? The Republica development split the apartments by allowing for more smaller ones. That helped in the sales of those, and part of the project has been sold to investors in groups of apartments, so that there was enough sales to be able to start. And for the demo location of Zoro, we are currently in the process of replacing buildings with others, additional PV, and we have to.
Hi, is everything okay?
To postpone the geothermal loop. So, why do I hear talking through the to my presentation? Okay, this is better. What do we else do? A city vision for all the parties involved to be developed in the course of the project. Based on a step-by-step methodology that originally comes from the Cities for Zero methodology developed by Technalia and Cartief. A lot of work is going on there. This is a very crowded sheet, but you can see in terms of the timing that we are now a kind of in the middle area of the sheet, which is the diagnosis of the various cities in order to be able to do proper planning in these city visions. An important challenge there is that each city has their own characteristics. Energy modeling requires a lot of data, and specifically in the fellow cities, this is not always available yet. And there is a huge difference in the starting point for each city. So to make it a combined effort is a challenge. As for Amsterdam, our activities in that city will more likely focus on how to implement and how to monitor the progress, because the city vision already was realized last year. Further, we have so-called innovation ateliers as an instrument for enhancing the speed of innovation. In essence, it is mobilizing a group of experts from various stakeholders, etc., to discuss issues around the positive energy district to better solve them, rather than that each stakeholder is in his own silo and tries to or sees the issues only at their own from their own side. Well, this is more to read later, because otherwise I will use too much time. Same for this one. Another important activity is replication and upscaling, in terms of assisting with a definition of what is a PET and what is the PET definition that we use, how to adapt solutions from the lighthouse cities to the others, and knowledge sharing from the lighthouse cities to the fellow cities. we have already achieved overviews of technological other barriers and so on to create overview of the city challenges and objectives so that they can be spread over the fellow cities. And in the fellow cities, pet areas have been chosen, and the evaluation of the baseline and technical solutions have started. Currently, in terms of capacity building, activities are taking place in peer-to-peer sessions and training sessions. Actually, one is going to happen next week in Amsterdam, where for the first time in more than a year, the fellow cities will also meet. This is for further reading. Our last topic on citizen-wide solutions is about citizen engagement. What has been done so far, as the construction and the developments are facing delays, is focusing on the models for how to optimize citizen engagement best. We are doing a number of things in that area, so to look at how residents envision their positive energy districts, and we're also working on energy citizenship and communities. The approach in general, it's important to understand that participation of citizens can be on very many levels, depending on the type of demos, the interventions, the city policy, the energy technologies context, whether that is acceptable to inhabitants or not. Tools are being developed for tackling the different levels of participation. And in the end, an activity program is being set up. And I'll have an example of such engagement plans for Amsterdam and Bilbao here, which is currently focusing on, at least in the Amsterdam side, on the lower levels of participation, like awareness raising in festival-like environment, an artistic intervention to start discussion among inhabitants, and walking and talking about energy and the climate as a tool. In Bilbao, it is already split up in low, medium, and high-level engagement, going from artistic creations, seminar, workshops, to citizen science activities for actual co-creation within Atelier. An overview.
You have to conclude now, please.
I'm rounding off. You can see in this sheet the different levels of participation that have been distinguished, and that the parties in the relevant work package are working on. And you can also see what are the hurdles, because we do not really have access to the future residents in the positive energy buildings. That is a hurdle, but we are also working on an implementation program already. So that is my last sheet in terms of content. And if you want to contact me, you can always reach me at my email address. So thank you for your attention.
Thank you very much, Rudy. So now we still have 3 more presentations to go, and we will hear from Jennifer Adami from Eurac, and she will talk about online energy matching platform. So Jennifer, could you share your screen, please?
Yes.
And yeah, try to be as short as possible. 10 to 15 minutes. Thank you.
So good afternoon to everyone. What I'm gonna to present is the new online energy matching platform that we are developing within the Horizon 2020 energy matching project, with the aim to support the renewable energy sources harvesting in buildings and districts. Just briefly, this project started in 2017 and is still running till 2022. The objective of the project is to maximize the renewable energy sources harvesting in the built environment by developing and demonstrating cost-effective active building scheme solution as part of an optimized building energy system. Among the several results of this project, there are the first two that are the energy matching tool, which is an optimization tool for PV in buildings, and the energy matching platform that is the focus of this presentation. The objective, in turn, is to offer the energy matching resources to support external stakeholders in integrating renewable energy sources in their built environment. And the strategy that we implemented is to create a sort of matchmaking tool into this platform to support users in finding the resources that are suitable for their own business. So specific content for specific stakeholders. And this matchmaking tool is based on a previous stakeholders analysis that we have performed. So clicking on this button on the landing page of the platform, the user can choose his own category, then the task that he has to perform, and then finally the platform suggests some specific sources that the user can find both into and out of the platform, but then later we will see. So basically, the energy matching platform has four main sections. The first one is dedicated to the energy matching tool to optimize the BIPV early design at building and district scale. The second one is a repository of BIPV case studies with also performance data available. The third one, the repository of solar window block configurations with performance data, again. And the fourth one, the marketplace section that shows technologies that are useful to integrate the renewable energy in buildings. So this is the landing page of the platform. Let's start with the energy matching tool. Basically, this tool aims to support since the early design stage of BIPV. It performs optimizations, not just simulation, but optimization to suggest the best BIPV configuration, meaning the PV capacity, the PV module's position, and the electric storage capacity for the specific case considered. And this tool is suitable to evaluate building to district scale because it is able to consider the energy sharing between buildings. So these are the input and the output of the tool. Among the input, there is the building geometry, the area that according to the designer is available for the PV installation, weather data, shading objects, the hourly electric demand, then costs, both for electricity and technologies, and then some features of the technologies. As output, as I anticipated, there are the optimal PV capacity, the optimal PV module position, the optimal battery capacity, and some key performance indicator about energy, economy, and environment aspects. Why we have this hourly electric demand as input of the optimization? Because this tool is basically is based on the hourly matching. It evaluates the hourly matching between the PV production and the building consumption. So it is able to calculate the expected energy that is directly self-consumed by the building. And then another aspect, important aspect of this tool is that we can run the tool using setting different target function. That could be, for example, to achieve the net zero energy building target or maximizing the net present value or and so on. So just to show you an application of this tool within this project, this is a multi-family complex in Sweden. On the left side, you can see the 3D model of the building with highlighted the areas available for PV. And then on the right side, there is the output of the tool. So the configuration suggested, the PV configuration suggested for this specific case. In blue, there are the PV modules suggested. More in a bit in detail, these are the input and the output. So there is the PV module efficiency, prices, cost of PV system, cost of battery, growth of electric demand or prices, then the annual discount rate, and then cost of maintenance and efficiency losses. And then as output, we have the suggested PV size, suggested battery size, cycles of the battery, PV system investment cost, the expected net present value and payback time. Then other indicator, let's say hourly calculated, that are the self-consumption and self-sufficiency, which consider just the energy that is directly that is produced and directly consumed into the building, so not passing through the grid. Then there is the annual cumulative production, the balance between production and consumption, and then the levelized cost of electricity and the specific emissions of CO2. And then we have also some charts. And this is the page on the energy matching platform related to the tool, where there are collected the input, the output, and some files. And among the files, we have a summary report of the optimization that the user performed, and then also the suggested PV configuration that, for example, a designer could download and then import it in his own project. So going on with the contents, we saw the optimization tool for Vipv, and now there is the repository of Vipv case studies. These case studies that are shown here are results of the energy matching tool application that the users decided to publish. So there are some filters to do the selection, to select which case study to see, about building scale, optimization objective, time horizon for the evaluation, cumulative annual energy demand, and the kind of supply, for example, heating, cooling, and so on. And then the performance indicators that are shown are the same as we saw in the energy matching tool. This is the page. You see on the top the filter selection, and then some case studies shown as a list and also as a map, on a map. Going on, there is the repository of solar window block configuration. First of all, the solar window block is an autonomous prefabricated multifunctional window system that integrates an insulating frame, a highly efficient window, a PV module, a shading system, and a decentralized ventilation machine. In this case, this section could not be further populated because it collects just results of simulation already done within the energy matching project. So no more simulation can be done, just the results are available. Also here there is a filter selection on climate, orientation, room type, glazing, and battery that is considered in the specific solar window block configuration. And then some performance indicators are shown relating to thermal performance, energy matching between production of PV and consumption of the ventilation machines, and then daylighting. And this is the related page on the energy matching platform. On the top, again, the filter selection. Below, you see 3 main configurations developed within the project, with the Vipv on sill, Vipv as overhang, and then Vipv on side of the window. And below, there are these results of the optimization. First, shown in a, let's say, more graphical way, and then with the specific data values. Finally, there is the marketplace section. This section offers an insight on the technologies that have been developed within the energy matching project that could be useful for the integration of RES in building and district. This part includes a brief explanation, some photos of the products that are shown, and first of all, some contacts, so that the user of the platform, the visitor, can directly reach the technology providers. This is the page on the platform. You see some technology providers, for example, of PV module, of heat pumps, of energy hub solution, and so on. Clicking on each component, you can have the specific sheet about it with, as I said, explanation, the contact, the reference contact, and then some photos. So this is more or less all about the energy matching platform. I would just add that more resources are can be reached from here. For example, we can reach the project website, the project catalog, where all the solutions developed into the project are shown, some basics about Vipv, and then some question and answers that can be useful. So, concluding, the energy matching platform provides resources at support of different stakeholders who want to integrate renewable energy sources in their built environment, or just to know more about the topic. Then the platform offers a set of performance indicators and allow users to evaluate several different Vipv and solar window block applications. And then it boosts the network among stakeholders and connect people to the industry. On the other side, the energy matching tool is a useful instrument to apply since the early design stages of building and district, as it provides preliminary suggestions that are useful for the later detailed phases of the PV project. And the tool considers the energy matching, the energy sharing, but is not ready to evaluate renewable energy community scenarios. So we still have to work on it. So this is just an invitation to try the energy matching platform and the energy matching tool. And maybe if you want to send me your feedback, because as I said, the project is still running, so we have a bit of time or resources to make eventual small improvement to the platform. So thank you for the attention.
Thank you, Jennifer. Very nice work, and thank you for your presentation. And now we'll jump to the other presentation from Alessandra Cuneo from RINA Consulting, which is in the room. And she will share her experience of Microgrid in Finland. So I don't know. Is this one or?
No. It was on the desktop, actually. This one?
Great.
Okay, great. So good afternoon, everybody. And I'm Alessandra Cuneo, R&D project manager at RINA Consulting, which is an engineering company based in Genoa, Italy. And today I will present you some innovation related to Tigon project, which is an European project dealing with development of direct current microgrids. And in particular, I will focus my presentation of one of the use cases that will be studied within the project, which is related to a residential district in Finland. Okay, this is just an outline of the presentation, so I will present you some challenging and objectives of the project as a whole, and then I will focus my intervention on the residential use case in Nantali district in Finland. So Tigon, in briefly, is a project that started in September last year. It's a 4-year project. It's funded under the call AC/DC hybrid grids for a modular, resilient, and high renewable shared grid development. So it's based on innovative solution for AC/DC hybrid grids. And is coordinated by CIRSE, which is a research center in Spain. And the consortium is composed by 15 partners that are relevant at European level and compose a multidisciplinary team from technology developers, manufacturers, end users, and of course a partner related to different transversal activities, and it's balanced between research centers, small, medium enterprise, and large companies. So which is the background of Tigon is related to the fact that alternative current historically dominated the power grids because the conventional generator were based on AC output, and the device at the end of the line were designed for AC inputs. But nowadays, with the increase of renewable energy sources and increasing the generators with direct current technologies, such as, for example, electrical vehicle or energy storage, there is the need to, let's say, switching the current grids and the current power grid scenario to a more efficient and reliable DC-related technology. So the objective is to, let's say, create a AC/DC hybrid grids that can enable and use better the DC-related technologies that are currently on our energy system. So the idea behind Tigon is to design and develop innovative DC-based grids architecture, which have the aim to improving the stability, the reliability, and the performance of hybrid grids, of course, in a cost-effective way. And for that, a series of technologies and solution, both from the hardware point of view and the software point of view, will be developed within the project, and all of them have the aim to optimize the control, the operation, and the protection of the grids. And one of the main, let's say, hardware components that will be connected the medium voltage DC grid to the grids is composed by the solid state transformer, which is actually one of the main important part of the project from a hardware point of view. Within the project, we have two main demo sites. The first one is in France. It's managed by SEA, and the aim is to demonstrating DC grids, how DC grids can enable an increased penetration of renewable energy sources in an efficient and stable and secure way. The second demo site is in Spain, managed by CEMAT, and here the aim is to demonstrating a smart and flexible management of medium voltage DC grids, which are linked to energy storage system and aiming to provide stability to the low-level hybrid grid. Upon these two demo sites, we have already identified two different use cases where the solution that will be tested, developed in the two demo sites will be, let's say, replicate in the use case. The first one is in Turku region, which is a residential district, and I will provide you more details in the next few minutes. And the second one is a use case in Sofia, where we would like to demonstrate how AC/DC grids could be helpful also in the railway sector. So not only our residential building, residential sector, but also on transport, on the transport section. So going focus on the use case related to the Finland Demo. Actually, the Finland Demo is composed by two main districts. One is in the Turku region, and the second one is in Nantali, which actually are very close each other. And within Turku, the aim is to study how the different solutions that are already installed, which are based on a shared use of solar photovoltaic power plants and a shared use of energy storage facility, can cover a larger part of the energy needs respect to having individual power plants. So we have different PV plants installed in the residential district together with a battery. And let's say we will see in the next year actually how this DC microgrid will work. The aim is to start the operation in September 2023. So now we are in the phase on design the DC grids and deploy and set up everything towards its demonstration. In particular, this is, let's say, an overview of the area of the residential districts. So we have, we integrate the photovoltaic power plants, energy storage system, which are connected to several houses through a smart low voltage direct current microgrid. And this microgrid will enable to use the energy which is produced by the PV locally to be distributed locally in a most optimal and fair way among the residents of the houses involved in the demo site, as well as to demonstrate and study the connection of EV charging station to the system. The second case, which is again in the Turku region, but is, let's say, related to another district, which is the Nantali residential district. And here, more or less, the solution is the same. So we have a residential DC microgrids at low voltage. And here, the solution are based on shared use of photovoltaic panel and energy storage facility that aim to cover the large part of the energy needs. And here, also, intelligent control and demand flexibility algorithms will be developed and deployed that, of course, have the aim to improve the degree of the cell consumption of the districts. Because, of course, the use of energy storage system can help to shift the production of the PV so that the energy can be consumed locally in the evening respect when, let's say, it is produced by the PV plant. And in particular, in the Nantali residential district, we have also the local DSO involved in the project, which of course an important stakeholder when we are talking about distribution lines and microgrids. And in particular, the fact is that within the Nantali residential district, we will study and analyze new schemes of demand response, which is based on the combination of the use of solar energy generation and the storage system in order to ensure the quality and security of the supply at electrical point of view. And the point of connection between the DC district and the main AC grids will be also considered as a mean to, let's say, integrate, if it's possible, we will see in the next years of the project, but the idea is to integrate ancillary services that maybe DC grids can provide to the national grid. So also to the aim of the Nantali district, which is actually one of the aim of the project, is to understand how the DC microgrids could provide services to the national grids in terms of ancillary services, but also in terms of improving the stability and reliability of the grids. So going into detail in the intervention that will be performed in this use case, of course, first of all, the model of the hybrid network will be developed, which of course will include the different assets in terms of electrical vehicle charging capacity, the PV energy production and the storage, and of course the Tigon energy management system, which is one of the technologies that will be developed within the project, will be adapted to the Turku region use case, and will include also the decision support system to support the design of the microgrids, and also different cybersecurity system, because actually the security of the grids is important. So within the project, cybersecurity measure will be developed and included in the software. And of course, everything related to the strategy for the optimization and the management of the renewable energy production. And in particular, in the last phase of the project, which involved the activities in Turku region use case, are related also to the development of new business case that involve low voltage AC and low voltage DC microgrids, specifically for residential application. In general, the last two slides are related to the key exploitable results of the project, which are, of course, results related to both technology solution, model, and software or strategy services. So we have the technology aspect in terms of the solid state transformer or the converters, or let's say the or the system. But of course, we have the different software key exploitable results. The fact is that the project will finish in 2024. Some of the results will be already marketable at the end of the project, which is a great, let's say, objective and achievement. While related to the technology, at the end, most of the key exploitable results will be aim to reach the marketability in 2-3 years after the project, which very close to at the end of the project. And as a conclusion of my presentation, so the expected impact as a whole of Tigon is to somehow, first of all, through the decision support system, try to provide guidelines to facilitating the planning of the grids, and specifically of the DC-based hybrid grids across the Europe, and let's say to enable a higher penetration of renewables into the power networks thanks to the DC architectures, and having at the end a more efficient electricity system, which at the end, if new configuration of DC-DC converters will be, let's say, developed and are expected, that this could help to achieve a high energy efficiency of the electricity system. So that's all from my side. Thank you for the attention. And of course, if you have any question, feel free to contact me. You have on all the slides also the email of the project coordinator if you would like to go into more details on technical aspects. Many thanks.
Thank you very much, Alessandra. And now the last presentation, it's Andrea Gabalon who will present a tool for the technology selection of PED. So you should click on the, Andrea, I don't know if you hear us. you should have a blue button to click on to share your screen.
Okay. Andrea, if you can hear us, we see you online in the session, but you need to click the button on the top right of your video that says share my audio and video. Andrea Moreno. Calling all Andrea Morenos. We can't do it for you. Oh. Who's that?
I don't know.
So Andrea, if you can share your audio and video, you can present. Otherwise, we'll need to close the session. I think we can take questions from the audience until you share your audio and video, Andrea. But you need to do that. We can't do it for you. Okay, so if there are questions online or here until she...
Yeah, sorry for this inconvenience. I don't know if in the room you have questions regarding the last presentations. No. And I have a look on the chat, and there is no other question on the chat. So yeah, Andrea, we are sorry, but we are not able neither to hear you or to see you. Okay, so if there is no questions, maybe we can close the meeting. So thank you very much. I want to thank the five presenters of tonight. And yeah, thank you very much all, and see you tomorrow for the other meetings. Bye.
Thank you. Bye.